your warm-up problem today, I basically forced you to figure out what the derivative of cotangent was. In our notes Friday, I tricked you into finding the derivative of tangent by using the quotient rule for sine over cosine. You will not have to do that anymore. If you get a cotangent or a tangent that you need to take the derivative of, we are going to remember what their rules are. We're going to remember that the derivative of tangent is secant squared x. We're going to remember that the derivative of cotangent is negative cosecant squared x. Okay? Also, I'm going to give you the rules for secant and cosecant. Those we can use the quotient rule to derive those as well.
Do those like co because their derivatives are negative? Because cosine has a negative derivative, cotangent has a negative derivative, and cosecant has a negative derivative.
I have no idea if that's why there's the co, but that would be a great way to remember your negative signs. All those co's have negatives with their derivatives. That would be a good way. I really have no idea how they make it, but I like what you're saying. If we wanted to figure out the secant or cosecant derivatives, we can use the quotient rule with 1 over cosine or 1 over sine to get those. That is a not very efficient way to find these derivatives every single time. We can do the quotient rule once and remember that this is going to happen. Okay. With these 4, we now know all 6 trig functions and a derivative. Okay? You have to remember that. Alright, I like Austin's suggestion about all of the co's have negative derivatives. Cosine is negative sine. Cotangent is negative cosecant squared. Cosecant is negative cosecant cotangent. Okay? If you look up there, tangent and cotangent, their derivatives have a similar pattern. Secant and cosecant, their derivatives have a similar pattern. Okay? You just have to remember these. Okay? So let's practice using them. What?
That's supposed to be multiplication, right?
No. The first one? The first one is just x minus tangent of x. Okay? Q, what's the derivative of x?
0. 1.
Which one is it?
1.
1. Okay? Minus the derivative of tangent. Isaac, what is it?
Cosecant squared x. There's 2.
I know, and it was in unison. Good job, guys. Okay? And that's it. We can't simplify that well.
I mean, you can take. Never mind. Do you take the derivative of the derivative?
That's what we will talk about in a little bit. Okay? Okay, so here's the deal. I would accept this answer, and this is the answer that I would expect from all of you. The back of the book may use the trig identity to reduce this down. Okay, 1 plus tangent squared equals secant squared. If you, wait, hold on. Am I saying that right? Yeah.
Secant squared is equal to tangent plus what? That's the same as c.
You're looking at an integral.
Oh,
Okay, 1 plus tangent squared equals secant squared. And so they would use that to rewrite this. I would not expect you to do that. And so with some of these trig derivatives, your answers could look different than the back of the book. I would encourage you to check CalcStat to see their steps as much as possible. I'm not going to make you simplify this down. I'm going to want 1 minus secant squared. Okay. How about part B? dy dx. What do we have? X secant x. We have a product, which means we have to use the product rule. Okay? So, derivative of the first times the second plus the first times okay, I'm getting differing opinions.
Oh, no, sorry, I see the x, multiply the x.
Secant x tangent x. Okay, so our derivative is simply secant x plus x secant x tangent x. Done. Any questions? Okay, this one does not involve any of our new rules, because there's just sine and cosine, but I think it'd be a good idea to get some more practice with the quotient rule, especially with trig functions inside.
Oh, just wondering, you know how you taught us that height before you said?
Yeah.
I did this on the magic school book.
We'll have to talk about that later. Okay. All right. So this is a quotient. We can use a quotient rule. Is there another way we can do it?
Yes.
What is that?
Do 1 over sine minus cosine over sine.
We could take the derivative of 1 over sine minus cosine over sine, which means what?
Cosecant minus.
Minus what?
Oh, cosecant.
Which one's going to be easier, taking the derivative of the quotient or taking the derivative here? All right. Derivative of cosecant. Josh, what is it?
Cosecant, negative cosecant x, cotangent x.
Minus derivative of cotangent. Jake.
Negative cosecant squared.
Okay. Now, if we would have taken the quotient rule, let's go ahead and just for practice, let's do the quotient rule. Okay, so our quotient rule. Low D high. What's the derivative of our numerator? What's the derivative of 1? 0. What's the derivative of negative cosine? Positive sine, okay? minus high d low. What's the derivative of our denominator? All over low squared. Okay. What we have is sine squared minus, if we distribute this through cosine, plus cosine squared over sine squared. Do you agree with my distribution? Okay. What can we do in our numerator? Anything? I wouldn't do that quite yet. There's one thing we need to look at. Is 1. Sine squared plus cosine squared is 1. Okay. Now, most of you are going to get to here and you're going to stop. And I don't have a problem with you stopping there. But the answer in the back of the book is going to be this. And so if you stop here and look at your answer, you may panic. Okay? Even though you did your work correctly. Okay? Why are these two the same?
Square root of x, and then if you separate the other two terms of negative cosine x over sine squared of x, you can separate cosine squared of x and sine squared of x and get cotangent of x, and we have 1 over sine of x.
Okay, so if you did the quotient rule, I would be happy with you stopping here. If you wanted to get the same answer as up there, you would have to go ahead and separate this fraction out. Okay, we know that 1 over sine squared is cosecant squared, minus cosine over sine is cotangent, and then we have an extra sign in the bottom. 1 over sine is cosecant. Okay, so we do have equivalent answers. They're just going to look different if you do them 2 different ways. Abram, did you have a question?
Yeah, if you go to like Calc Chat, what answer will it have?
Calc Chat's going to go as simplified as you can go. Okay, so if you do a quotient rule, just make sure that when you simplify your quotient, it looks like this. Most of the time, they will have, like if there's more than one way to do a problem, most of the time, and I say most of the time, they'll have both ways, but I wouldn't guarantee it every time. So if you have a question on if your way is legitimate, just ask me the next day. Okay? Okay. This is where it gets fun. Okay, so our first derivative, I haven't been calling it that, but it's called the first derivative because there's more than one kind of derivative. Okay, this has been our notation, y prime or f prime of x or dy dx. Okay, we can take the derivative over and over and over again. That's what Cole was asking earlier. Now, only the first derivative stands for of our function. Okay? Once we take the second derivative, we're talking about the derivative of the derivative. So all the relationships we were talking about earlier, those still exist between the first and second derivative. Does that make sense? This is the notation for the second derivative. You're basically just going to add a tick mark, okay, or d squared y over dx squared. Okay, so the second derivative represents the slopes of the first derivative. The second derivative represents the slopes of the first derivative. We still have that same relationship, but we're just talking about from first derivative to second derivative. Okay. Our third derivative notation looks the same, except we now have 3 tick marks. Y triple prime. Once we reach the fourth, well, first, the third derivative represents all of the slopes of the second derivative graph. Okay. The second derivative represents the slopes of the first derivative graph. Okay. Once we get to the fourth derivative, we know we're not going to put 4 tick marks. Okay, that's going to get a little too crazy. So we'll just put a parentheses with the number 4. Okay, and any higher order derivative after that, we would do the same thing. So once we reach the fourth derivative, that and anything higher, we're not going to put tick marks, we'll just put y to the parentheses n. Okay? And same thing here with the f of x notation. Okay? Our derivative still means slope of the tangent line or instantaneous rate of change. But if we're talking about the second derivative, it represents the instantaneous rate of change of the first derivative. No longer of the function, but it's just the one step below, okay? Whatever we take the derivative of, okay, it represents that instantaneous rate of change, okay? So what's going to happen is we can find the derivative. To find the second derivative, we'll take the derivative of the derivative, okay? To find the third derivative, we'll have to take the derivative of the second derivative.
Will you ever give this like f of x and how it's defined as both derivatives?
Yes. However, we'll talk about some. If it's polynomial, yes, or like if we take the derivative of sine of x, it's going to flip back and forth between sine of x, cosine of x, sine of x, cosine of x. So there'll be a pattern. So you won't actually have to ever find all 12 derivatives. There will be ways for patterns, and I'll talk about that here in a little bit. Okay, go ahead and write this one down. Okay, y equals x cubed minus 5x squared plus 6x minus 4, and we're going to find the fifth derivative. That's what that means. Some of you might have an idea of what it's going to be. If you have an idea of what it's going to be, turn to your neighbor and tell them your idea. Cole, what do you think it is?
I didn't say that. I said
What did Isaac say?
he said, let me write it down with wrong. Cool.
Okay. Any ideas before we start of what you think it's going to be?
0.
Larry thinks 0. Okay. Larry, help me with the first derivative.
Oh my gosh. Okay, let's do this. Okay, don't worry. 3x squared. Minus 10x plus 6. 0.
Excellent. Thank you, Larry. Okay, let's work on the second derivative. Okay. Josie, help me out. Great. Our third derivative. Trevor.
Would just be 6.
It would just be 6. Our fourth derivative. What's the derivative of a constant? Okay, Larry, will come back to you. What's our fifth derivative?
0.
Larry was wrong. Okay, Larry, can you tell us why you thought 0 to begin with?
Because the x value keeps going down every time, so I just started.
Okay, we started with an x cubed. Every time we take a derivative, we decrease a power, right? There weren't enough powers to take all of our derivatives, right? Larry knew we were eventually going to run out of x's, and it would probably go to 0. Okay? Good idea, Larry. Now, Cole, let's come back to your question. What if I told you, y equals x to the 12th, and I told you to find the 12th derivative? Okay, let's talk about our thought process for that. What's going to happen with each derivative? The exponent's going to keep getting smaller, and what happens with our coefficient? Okay, and there's a pattern, right? Our first derivative is going to be 12x to the 11th. And then our next derivative is going to be 12 times 11 x to the 10th. And then our next derivative is going to be 12 times 11 times 10 x to the 9th. You see where I'm going here? Okay. So if I'm asking you for the 12th derivative of x to the 12th, what power is x going to have? What power is our x going to have? Cole says 1. Q says what? Sorry, you're right next to each other.
0.
X is going to have the 0 power, so it's just going to be the coefficient, right?
Yeah.
Is there a way to express 12 times 11
Factorial.
times...
Factorial.
Huh?
Q.
Yeah. Cole, I'm really glad you brought it up because there will probably be a multiple choice question on like the non-calculator portion that would be like that, where you have to think about the pattern, okay? And so yes, you would have to use.
Okay.
You have to think like that. Okay, last example, and then you're gonna get some work time here. I have a table of G, G prime, F, and F prime at 2 different values, okay? So you see here are my X values for F of X, F prime of X, G of X, and G prime of X. And what I want to find is the derivative evaluated at 0 for H when H means F divided by G. Okay? So don't feel like you have to copy down the table unless you really, really want to. What's important here is that our H function is F of X divided by G of X. If we want the derivative at 0 for H, what are we going to need to do first? What, Abram? Oh, okay. Before we can evaluate the derivative, what do we need? Before we can plug a number into the derivative, we need the derivative. Okay.
The derivative status. Oh.
If H is F divided by G, what do we need to use? The quotient rule. Our quotient rule is low D high minus I D low all over low squared. That's as basic as you can get. That is just copy paste the quotient rule. We really didn't even have to apply it to any functions. Okay, that is just the quotient rule. Okay, so now if we want h prime of 0, then we are just going to plug 0 in everywhere. So f prime of 0 times g of 0 minus f of 0 times g prime of 0 all over g of 0 squared. How will we figure out what all of these values are? How will we figure out all of these values? Look at the chart. Which I wrote too big. I'm going to have to scroll back and forth. Okay. Looking at the chart, what is f prime of 0? -3. Remember to use parentheses. What is g of 0? Minus. What is f of 0? Times g prime of 0. All over g of 0 squared. What is g of 0? What is g of 0? 5. Thank you. So we have -15 plus 2 all over 25. H prime of 0 is -13/25. This is what I call a problem that uses tabular data. There is data in a table where we have to pick and choose from to evaluate our derivative. Okay? This will not be the first time you see something like this. Not only will it be in your homework, but this is a very popular AP question as well. Okay? So you have bookwork on your gold sheet. These are the problems, but it's also on your gold sheet. Yes? Sure.